Hi there, I'm Mr. Manoj, and today the video presentation is for AS Chemistry students 9701 syllabus. I'm discussing the paper 22 of 2016 exam series. So as I begin to start discussing this paper, preferably why don't you grab a couple of blank sheets, calculator and data booklet, and if you could solve the question ahead of my video, and once you finish a particular question, you could pause the video and have a look. First you solve, and then you can check back with my video and check how well have you performed, and pick up any hints or explanation if you need any. Alright, so let's have a look. This is 2016 paper 22. So let's have a look at the first question. Okay, so the question talks about there is some mass given there, and it talks about some group 2 metal. There is hydrochloric acid information, we got the volume information, we got the concentration of the acid. We've also been given some kind of a mole ratio between the metal and the acid. You must also keep a note that they clearly said acid is in excess. Now don't forget, if acid is in excess, which means this is the limiting reagent, that's the one who's controlling the whole reaction, which means the amount of gas produced depends on the M which is present here. Alright, the first question talks about to find out the moles of the acid given. Well, you got the volume, you got the concentration, so I'm sure you remember the formula N equals to C times V. So I got my concentration, which is 1.00, and the volume is given in 40 cm cube. Now don't forget, we can't use that in our expression. The cm cube, we need to change that to dm cube by dividing it by 1000. So should we just work this out and see how much you get? When you work this out, you get 0.04 as your answer there. Now we got the moles of the acid. Remember, this is the excess amount of acid which is present. Then the question talks about that 10 cm cube of this acid was taken, which is so much moles. 10 cm cube of that was taken, and into a volumetric flask, and then we added more water to make a total volume of 100 cm cube. Now remember, this is the diluted acid, which is being prepared by adding more water into this concentrated acid. And then from this 100 cm cube, 10 cm cube was taken, and it was then reacted with sodium carbonate, and the information for sodium carbonate is given here. We got the volume and the concentration used. Okay, now the first question talks about we need to write a reaction between sodium carbonate and the acid. Well, to work the reaction out, this is a simple reaction which you might have studied in the IGCSE level. Sodium carbonate is Na2CO3 that reacts with acid. You remember the acid reacts with carbonate to form salt plus water plus carbon dioxide. So the salt Na combines with Cl, and keeping in mind that the valency of Na is 1 and the Cl is 1, so it's NaCl, that's salt plus water plus carbon dioxide there. Now don't forget to balance the equation. I have 2 sodium here, and to make this 2 I need to put 2 in front. Now because of that, my chlorine got changed. I have 2 chlorines there, so to balance I'm going to put here 2. That makes my hydrogen 2, so I'll check here, the hydrogen is 2, which means the oxygen also should be balanced. Well, the next question talks about find the moles of sodium carbonate that you think would react with 10 cm cube of the acid. Remember, this is the diluted acid. Well, you have the information about the volume of the carbonate and the concentration. So to find the moles, since you have all the information, so moles equal to C times V. So the concentration is 0.05 times volume is 15. Don't forget, this also has to be divided by 1000. So when you solve this out, you get 7.5 into 10 raised to power negative 4 moles as your answer there. So that's the moles of sodium carbonate that was reacted. Now the question says, use that information to figure out the moles of the acid present in the 10 cm cube. Now remember that reaction happened here. The ratio between them is 1:2, I got the moles of sodium carbonate. So I have the moles of sodium carbonate. I need to find how much acid was there. So I'm going to use that mole ratio. So I have moles of sodium carbonate ratio moles of hydrochloric acid. So from the previous question, I know it's 1:2. We also know that the moles of sodium carbonate is 7.5 into 10 raised power -4. So I'm going to take that information, and that's basically the unknown. So to find the value of x, I just have to take the previous answer and just times it by 2. So when we times this by 2, we end up getting, so I have 1.5 into 10 raised power -3. There you go, -3. So that's the moles of the acid present in 10 cm3. Now don't forget that is 10 cm3, which was taken out of 100 cm3. Now the question says calculate the moles of the acid remaining after the reaction shown in 1. So you see, if this is the what this means is how much is the acid left over. This is the acid present initially, and then we diluted that acid and we used 10 cm3 of that and reacted with sodium carbonate. And this is the amount of moles of acid present in the 10 cm3 of the diluted. So first of all, what we can do is, so you could think of this way, that in 10 cm3 of the diluted, the acid present was 1.5 into 10 raised power -3. So that's the amount of acid present in 10 cm3. Now, how can you use that information to figure out how much was the acid present in 100 cm3? So the acid present in 100 cm3 would be, you could put an x and cross multiply. That's why, or you could just understand that's the previous answer times 10. That's how you basically end up getting 1.5 into 10 raised power -2. That's the answer there. That's the amount of the acid in the 100 cm3 which was left after the reaction. The question now says, okay, use your answers of the previous questions to find the moles of the acid that actually reacted with the 0.5. Now remember, this means this is the initial amount of the acid left, which was there, 0.04. And this is the amount of acid which is now left in that solution, which means how much do you think got reacted would be the difference of the two. So that's going to be like 0.04 minus this is 0.015. So let's see, it's 0.04 minus 0.015. So that's how we get the answer as 0.025 moles. That's the answer there. And then use this answer to find the moles of M. Now this is the moles of the acid, the actual that reacted. So let's go back to the first question. Yeah, this equation there. Now I have the moles of the acid. I can use this to find the moles of M. You see the ratio is 1:2. So I'm going to use that here to find moles of M. So M ratio acid was 1:2. So I have the acid as 0.025. So that's X. So which means X should be 0.025 divided by 2. So that's basically, yep, we get 0.0125 moles as the answer there. And we have to use that information to find the AR of the M. Now for that, if you go back to the question, you'll notice that the question talks about the mass of M was 0.5. So I have the mass 0.5. And I have now the moles. So to find the mass, we formalize moles into AR. So I'm going to take the previous answer 0.0125 well, AR, so that's what's missing, and the mass is given as 0.50. So I can rearrange this to get the AR. You could also use the formula AR equals to m by n. So I have the mass 0.50, I have the moles 0.0125. And if you do that, so that's 0.5 divided by 0.0125 gives the answer as 40. So we get the AR as 40, and if you look at the periodic table, then that belongs to the element calcium. So that's basically how to solve this question. Okay, so let's have a look at the second question. Why don't we read the question a bit by the time why don't you pause the video, try to attempt this question, and then once you finish, then try to check back and see how. Let's have a look at the second question. We have here an equilibrium established between N2O4 and NO2. Enthalpy change is positive 54, which means the forward reaction is endothermic. Energy profile diagram is mentioned, and the question talks about add labeled arrows to the energy profile to indicate enthalpy change. Well, enthalpy change is the difference between the energy of the reactant and the energy of the product. So that's basically this difference here is the enthalpy change. So I'm going to label this as delta H. And the activation energy for the forward reaction, that's basically the start of the sketch to the height of the peak. So it should be an arrow which is usually drawn vertically up. That's from here to here. That's the energy required. So that's the 2 marks there. And then the question talks about the moles of N2O4 is mentioned, and okay, the volume is mentioned, temperature is mentioned, pressure is mentioned, and even the mass is mentioned. So if you have all this data, you probably should think of ideal gas equation, because you have everything mentioned there. And you're supposed to find the average molecular mass. Well, you might remember PV equals to nRT, but instead of n, I can do m over mr RT. And then since we have to find mr, so I can make the mr the subject. So mr equals to mass times gas constant times temperature divided by pressure times volume. So the mass is 4.606. The value of 8 is, R is 8.31. Don't forget the temperature must be in Kelvin. That's 50 degrees. So that's 50 plus 273. That's to change to Kelvin. Divided by, don't forget, if the pressure is in kilopascal, the volume has to be in dm cube. Or if the pressure is in Pascal, the volume has to be in meter cube. So you need to pick up one of these two. So I see pressure is in Pascal, so I'm going to take the pressure as Pascal. So 1.68 into 10 raised power 5 PA. Now, since the pressure was in Pascal, I'm going to keep the volume in meter cube. The volume here is in dm cube. Now don't forget 1 meter cube. 1 meter cube is 1000 dm cube. So if I want to change dm cube to meter cube, I need to divide this by 1000. So that's why that 1 dm cube, if you divide by 1000, it becomes 1 times 10 raised to the minus 3 meter cube. So now I have everything correct. Remember, I can keep the volume in dm cube, but I must keep the pressure in kilopascal. Alright, so when you punch in all the numbers and see what you get, you should get answer as 73.6 as your answer that 0.05 plus n. So when I solve this, that should come out to be 0.02 plus 0.4n. So that's 2n. So 2n minus 0.4n should be equal to 0.02. Keep solving out and you will get the value of n as 0.02. 0.0125. Now once you get the value of n, if you look at the equation here, you solve that the moles of NO2 was 2n. So I'm going to take that information. With moles of NO2 was 2n, so that's since it was 2n, so that's 2 times the value of n, which is 0.0125, and that's why the NO2 works out to be 0.0125 times 2 should work out to be 0.025, and for N2O4 that was for NO2. For N2O4 we had it here. The moles of N2O4 at equilibrium was 0.05 minus N, so 0.05 minus N. So when I do that, that's 0.05 minus 0.0125, and that's basically how we get 0.0375. There you go. That's basically how we solve this question. We need to write the expression for Kp. Remember, Kp equals to partial pressure of the product, which is NO2 raised to the power 2 divided by partial pressure of N2O4, which is on our left hand side. So always remember, if you look at the equation there, total pressure, and you're supposed to find the Kp value. Now remember, the Kp expression is here, and this basically means we need partial pressure of NO2. So before we do any calculation, I need to find partial pressure of NO2, which is actually mole fraction times total pressure. Now the mole fraction happens to be the amount of NO2 at equilibrium, which is 0.025 divided by the total moles at equilibrium. So I'm going to have to add these two together here to find the total. That's a 0.0375 plus 0.025, and that gives me 0.0625. And then I need to times this with the total pressure given, which is 1.68 into 10 raised power 5 Pascal. So that's the partial pressure of NO2. And then if you look at the Kp expression, the partial pressure of NO2 is raised to the power 2. So if I'm going to just carefully put everything, and that's raised to the power 2, and I'm going to divide this by the partial pressure of N2O4. Now the partial pressure of N2O4 will be calculated the same way. The amount of N2O4 is 0.0375. This is 0.0375 divided by the total of these two, which we already did here, which is 0.0625 times the total pressure, 1.68 into 10 raised power 5 Pascal. And so that's basically what I have to do. I need to solve this out. There is no power to this one, and once I solve this whole thing out, and eventually since the answer is in PA, I can get the answer as let's try this out. So that's a 0.4 times 1.68 raised to power 5. So this could be, and then square it, and then divided by 0.6 times 1.68 times 10 raised to power 5, and this comes out to be 444800 Pascal. And of course, if you want to report this as kilopascal, you can divide this by 1000. So that will be, if you want in kilopascal, that will be 44.8 kPa or 44,800 pascals. So I'm going to keep the unit as PA at this point of time, because we've been working with, because this is PA raised power 2, this is PA, so they cancel out and 1 PA will be still left. So you have a choice to report the answer in Pascal or in kPa. So that's how you solve this question. So I'll give you some time to have a look at the next one. Okay, let's have a look at question number 3. This question is from your topic 2, ionization energy trends, and what we're looking at is how the ionization energy trends move in period left when you go from left to right. This is basically lithium. This is period number 2, lithium going to neon, and then this is sodium starting period number 3 going up to argon. So that's something that you study in topic 2. And the question talks about why do you think generally there's an increase in the ionization energy from sodium to argon when you go left to right. Well, the general comments would be when you go from sodium to argon, the number of protons increase. So if the number of protons increase, don't forget that's going to increase the nuclear attraction, and that's why the electrons are bounded more strongly to the nucleus, and you'll find it difficult to remove the electrons away. So if the number of proton increases, the nuclear charge, the nuclear attraction, also increases. So that's a very simple way to understand this question. Since it's only worth 2 marks at this point of time, so that will be enough. So the number of proton is increasing. Instead of that, you could say nuclear charge is increasing. That is accepted. And so because of that, this happens. So each is. Have a look at this question. It talks about why do you think there is a decrease in the ionization energies between atomic number 12 and 13? So if you look at the graph here, we have sodium as atomic number 11, magnesium is 12, aluminium is 13. So you see there's a decrease in the ionization energy, and we need to understand why is that happening. So what we're going to do is, if you write the electron distribution for aluminium, and that comes to be 1s2, 2s2, 2p6, 3s2, and 3p1. So that's the valence electron for aluminium. And if you look at magnesium, it comes out to be 1s2, 2s2, 2p6, and 3s2. So that's the electron distribution for magnesium. Now clearly you see that aluminium, if you count the subshells, 1, 2, 3, 4, 5, and this one has 1, 2, 3, 4. So aluminium has more subshells, which means it will have less shielding, more shielding effect. More shielding effect means less nuclear attraction. Also keep in mind that the electron of aluminium is at 3p, which is at a higher energy level compared to 3s of magnesium. So the 2 main reasons why aluminium, you find it much easier for you to pull the electron out from aluminium. So you could say that the aluminium has more subshells. You could say that. It's always good to have a clear, much more, an answer which explains a bit more clearly. As compared to marking schemes, don't forget they are basically for teachers, not for you. So you need to be, construct answers which reflects your personality, your age. So try to write in a very easy, simple language. It's easy for teachers to correct, and of course, the main idea should be there in the marking schemes. So aluminium has more subshells, so because of that, therefore, it has more shielding effect, and that will explain the less nuclear attraction, and also the 3p electron, electron of aluminium is at a higher energy level. Now, because it is at higher energy level, that is why it's less stable and therefore easy for you to pull the electron out with higher energy level. Okay, now this question here, it talks about elements atomic number 2, 10, 18. So let's have a look at who these elements are. Atomic number 2, well, it's talking about this one, which is helium. Atomic number 10, this is neon. And atomic number 18, this is argon. So clearly, what we are looking at is we are going from helium to neon to argon, which means we are actually going down the group. And the question is indirectly asking you, why do you think the ionization energy decreases as we go down the group? Okay, so let's have a look at that. So to explain, this question is only for 2 marks. It could be worth 4 marks also in the previous case I have seen. You have to highlight the fact that as you go down the group, the number of shells size definitely is increasing. So that's definitely one thing you can speak about. And the number of shells and the subshells are increasing. So the shells and the subshells increase. So because of these two, clearly the ionization energy must decrease. But then as you go down, there is also increase in the number of protons. This is one factor which you must keep in mind. And as the number of protons increases, the nuclear attraction has to increase. Now, what happens is, because of this, the nuclear attraction which is increasing is actually overcome or countered by these two factors. So because of that, the ionization energy overall actually becomes less. So remember, the important things that you must mention here is, as we go down, the size increases, shells increases, subshells increases. That contributes to decreasing of the ionization energy. But the increase of nuclear attraction caused by increase in the proton is overcome by these two factors. So that's a good way to write. Alright, let's have a look at this question, which is B part. This is a melting point graph. This comes from topic 4 of your syllabus. This is basically sodium, that's magnesium, aluminium, that's silicon there, and we have phosphorus, that's sulfur, chlorine, and argon. Okay, so that's everything is there from topic 4 of your syllabus notes. General question, why do you think melting point is increasing from 11 to 12? This question is talking between sodium and magnesium. Why do you think there is an increase there? Well, the main points what you could talk about is sodium and magnesium, they exist as ions, and the size of the ions, which is your ionic radii, ionic size actually decreases from sodium to magnesium. So the magnesium ion is smaller in size, and don't forget the charge on the magnesium is 2+ compared to 1+ on sodium. So the magnesium ion is smaller ion, it has got double positive charge, it's got high charge density, as we say, and that contributes to the increasing in the strength of the metallic bond, and that's why the melting point of this is more than this. So that's the good answer there. And then it talks about why there is the increase from atomic number 12 to 13 is much smaller than the increase from 11 to 12. So what this question was talking was, when you go from sodium to magnesium, there's a huge increase in melting point, but when compared to magnesium and aluminium, that increase is not as big as compared to here. Why do you think that is? Well, you could base your answer based on the size of the ions. Now, there's a huge difference between the magnesium ion and the sodium ion. Sodium ion is significantly much larger than the magnesium ion. But then between these two, the difference of the size of the ions is not that great. So you could say that the iron size difference between these two is much more than compared to the difference in the size of ions between magnesium and aluminium. So that's the reason why this change is not very dramatic in these two compared to this one. So that's basically a simple answer. This you could just say that the difference in size of the ion is too much when it comes to magnesium and sodium, but less compared to magnesium and aluminium. You could quote your data booklet ionic radius page for that. This question talks about explain why the element with atomic number 14 has a melting point so much higher than the rest of the element. Now, if you look here, that's silicon. So you must remember something about silicon is in group 4. It's a macromolecular structure. It has strong covalent bond around it. You might remember each silicon is bonded with another 4 silicon. So that's the kind of structure what silicon crystals have. It's a macromolecular tetrahedral structure, and that's what makes it so strong. So that's it. That's the 1 mark question. So just say because it has a macromolecular structure with strong covalent bonding, and that's why the melting point is very high. Alright, so that finishes question number 3. So I'll give you some time now to have a look at question number 4 before we. Okay, so let's have a look at the organic chemistry question. This question talks about name this compound. Well, I see there's a bromine there at second carbon, so that's carbon number 1, 2, 3, and 4. So that's why this is going to be 2 bromo, and I see there are 1, 2, 3, 4 carbons, so that's 2 bromobutane. And also this particular carbon here is a chiral carbon because it has, that's 1, that's 2, that's 3, and that's 4. So it has 4 different things. So that is why this question talks about the stereoisomerism shown. What they were mentioning was the optical isomerism due to the presence of chiral carbon. So when you want to draw the optical isomerism, so you could, don't forget tetrahedral, also some kind of shading. There we go. And then do the exact opposite here. Now I have HBr CH3, so I can put it anything I want. I'm putting H here, and I'm putting the Br here, then the CH3 here, and I have a CH2 CH3, so I can write C2H5. So I'm putting CH2 CH3 here this way. So once I finish there, that's the mirror image, which means the H remains here, the Br comes in here, CH3 comes in here, and this becomes CH2 CH3. That's my 2 optically active isomers. Remember, optical active isomers are the ones who are able to rotate the plane polarized light to the right or to the left. We don't have to know the details of that in the AS syllabus. Alright, my next question talks about for us to make 3 different structural isomers of C4H9Br. Keep in mind that already we have one of them on the top, which is 2-bromobutane. So we need to draw 3 other structural isomers. So since that's 1-bromobutane, so I can think of that's 2-bromobutane, so I can think of making 1-bromobutane. So I can connect the Br here, so that becomes 1-bromobutane. So don't forget 3 H's, 2 H's, 2 H's, and 2 H's. That's 1-bromobutane. I can even think of a carbon with a Br, and since I have 4 carbons, so I can think of something like this. That's another structural isomer. I can even think of a 3-carbon chain with a carbon here and a Br here. That's going to be a CH3, that can be a CH3, that's an H, and that, that's an H2. So this could be 2-methyl 1-bromopropane. This is 1-bromobutane, and this is 2-methyl 2-bromopropane, and this is 2-methyl 1-bromopropane. So that's the 3 different isomers compared to the 2-bromobutane which we made here. This question here talks about try to name this compound. So it's always good if you could open the structure of this and see what it's made of. It has 3 C2H5. So I'm going to put a C2H5 here, and I'm going to put a C2H5 here, and a C2H5 here, and then I have a Br. Now when I do that, I understand that that's my parent chain, which now has 5 carbon atoms, and that's carbon number 3. Now carbon number 3, I have a bromo group on carbon 3, and this is the ethyl group on carbon 3. Now out of ethyl and bromo, Br comes first. So that's why it's going to be called as 3-bromo 3-ethyl pentane. So 3-bromo 3-ethyl pentane. That's the answer for this question. This reaction mechanism is from topic 16 of your syllabus, the halogen alkanes. If you notice here, this is a carbon with Br and it has no H. It's a tertiary halogen alkane. And tertiary halogen alkane, they undergo a reaction mechanism called SN1. Remember, the primary undergoes the SN2. This is SN1. Now in an SN1 mechanism, basically what's going to happen is Br is electronegative, so it's going to pull the electron pair towards itself. So Br becomes partial negative and the carbon becomes partial positive. And then this particular bond breaks away, and so this is what you get, the CH3 CH2. Then there's a carbon, and then there is a CH3 CH2 is here, and there is a CH3 CH2 is here, and this carbon is now a plus charge. That because the pair of electron has shifted to bromine. That fission is called a heterolytic fission. That basically is the reaction intermediate, and now the Br is out with it, and the OH minus now, that's nucleophile. The curly arrow will go this way, so that's the new dative bond which is being formed. And so when everything gets okay, the bond is made. So I have a CH3 CH2 C. I'm just going to put C2H5, and this is C2H5, and then the OH comes and connects. Don't forget the Br which has been kicked out is the leaving group. That's the nucleophile which has been kicked out. That's basically SN1 mechanism. So because this question is what type of reaction mechanism, so that's why SN1. The reason we call it SN1, because in the reaction intermediate, you see there's only one reactant here, and that's the one which controls the rate of reaction as well. Now this question talks about how would you convert this compound into a mixture of alkenes. So that's the halogen Br, and I have to remove a H and a Br to get an alkene out. Now if I see here, this carbon has 3H and this carbon has 2H, so I have to remove the H from this one and the Br from this one. So the double bond has to come here. But of course, don't forget, I can remove H from here as well. So what reagent and conditions. Now to get this halogen and the hydrogen out, the name of the reaction is elimination, and to do that my reagent is usually sodium hydroxide or potassium hydroxide, but they must be dissolved in ethanol. So they are dissolved in ethanol and heated. So that's basically how I'm going to get the hydrogen and the halogen out. So hydrogen goes from there, H goes from there, I should get the double bond there. And then this question talks about give the name of the mechanism. Well, this is called elimination. That's an easy name to remember. Sometimes in multiple choice question you might come across the word dehydrohalogenation. That's because a hydrogen and a halogen was removed. Here the question is about how could you draw a skeletal formula of the three alkanes you think that could be produced here. Now when you remove the H and the halogen, I should preferably get the double bond between carbon 2 and 3, and that's basically pent-2-ene. So that's a 5 carbon chain, and I should preferably get the double bond between these two. The other possibility would be I can get the H removed from here and the Br from there. Then the double bond should come between these two carbons, which means I can have a 5 carbon situation where the double bond is between first two carbons. The third alkene, actually, if you notice here, this is pent-1-ene. This doesn't show me the geometrical isomerism cis-trans because it has the two identical atoms on it. So my first isomer, let's say I'm going to put this one, pentene, 1, 2, 3, 4, 5. I'm going to put the double bond here, and that's it. The other two isomers, now that's coming from pent-2-ene. Now pent-2-ene, if you notice carefully, this one has an H and a CH3, and it has an H and a C2H5. So that's two different things on each of the carbons, so it means it can form cis-trans isomerism. Now cis-trans isomerism means I can think of something like that. Now when I design the alkene this way, now this one has an H and it can have a CH3, and this has an H and it has a C2H5. So that's what it is going to look like. So that's basically cis. And then I can swap this H's to form the trans. The trans, obviously, the H comes in here, CH3 comes in here. So this arrangement is called as the trans isomerism. Then the question said you need to draw this in skeletal formula format. So if you look at that, and then you could design your, it's much easier for you to work. So it's 1, 2. So that's carbon number 1, this one, that's carbon number 2, and that's the double bond. And then I want to show cis. It means let's say, I can show it this way, and then I can show this. So it's 1, 2, 3, 4, 5. So it's 1, 2, 3, 4, 5. So that's basically cis isomer. You see, this and this is on the same side, so that's a cis isomer there. And then to make the trans, which is this way, so I'm starting here. So that's 1, 2, 1 carbon, second carbon, and so let's say I go this way, and then I have to show trans, which means I can go 1, 2, 3, 4, 5, and that's this. This is going up, that's coming down. So that's basically, this is a trans isomer, and this is on the same side, so it's a cis isomer. So that's basically how you could solve this question. Find two particles which are produced when methane and chlorine react in the presence of ultraviolet. Now this is from your topic 15, where you study free radical substitution reactions of alkanes, and you study methane and chlorine reaction there. And you might remember when these two react, you get free radicals. So you get chlorine free radicals, so that's the Cl dot, and then you also get the methyl free radical, which is the CH3 dot. And in those mechanisms, you never got the ions, and you never got the H free radical there. Two particles you would get in a heterolytic fission of a bond in a chloromethane. That's basically a CCl bond. In a heterolytic fission, remember, both the electrons are going to be with the more electronegative. That means I should get a negative ion and a positive ion. So I should get a negative ion, which is Cl minus. And now once the electrons have been pulled away, this carbon picks up a plus charge, so I should get this one. This is called carbocation, so CH3 plus. So that's the good answer there. And then this question talks about there are 4 kind of reactions mentioned, and we need to pick up the right word which matches that reaction profile. Tolerance reagent, well, this is topic 18. Aldehydes and ketones is used for testing the presence of aldehyde. It's a mild oxidizing agent, and therefore when it reacts with aldehyde, it oxidizes the aldehyde, and tolerance reagent undergoes reduction. So it's oxidation reduction reaction. So I have oxidation here, separately given, I have reduction, but they're not given together. So I can say oxidation. I will be allowed to say reduction also for the same thing. And for this question, if you want to test aldehyde carbonyl group with 2,4-DNPH, the thing is, it moves the double bond O of the aldehyde and ketone. It uses this H to create the vacancy there. So the H and the O go out. So that's why it's called as the condensation reaction, because there is elimination of water which is happening in this equation. The third question talks about the reaction between ketone and NaBH4. This is reduction of the ketone. You might remember secondary alcohol oxidizes and forms ketone, and this is reduction of ketone back into secondary alcohol. So that's why reduction would be the most correct answer here. Name the type of reaction involving reaction of aldehyde and hydrogen cyanide. This was nucleophilic addition. But then they didn't say nucleophilic addition, they only mentioned addition here, so just addition would be fine. But the correct name is nucleophilic addition there. And, I hope you enjoyed this video presentation. I hope I could help you in some questions you might have found it useful. Please send in your comments, your suggestions. If you need any specific topics for me to discuss on, or any improvements I could make. Your suggestions are always very helpful. Don't forget to share it across your different social media platforms to help as many students as possible. And I hope to make some more videos in future. So very shortly, some more videos for AS level is going to be put up soon. All the best for the incoming examinations for the students of May, June, and a big shout out to all my students as well. God bless you, and till I see you again.